Hello. In this video, we're going to discuss the pharmacology of basically drugs that target electron transport chain and ATP synthesis. So this is a general scheme. We have complex 1, complex 3, complex 4, and of course ATP synthase, also called complex 5, although ATP synthase is not part of the electron transport chain. We've already discussed uncouplers. We discussed DNP, dinitrophenol, there's dicumarol, FCCP. All they do again is open a hole, okay, on the membrane, so they create a short. Okay, so then you have electron transport chain, shown here in the gray box, but you cannot produce any useful work because the voltage across the membrane is equalized. So there is no movement of protons to drive ATP synthesis in ATP synthase. But you respire. The electrons keep transferring onto oxygen. Okay, you just don't make any ATP. So this is exactly analogous to a short in an electrical current. Now, what if? Okay, so if you have a short, what do you get? You get heat, right? So it's possible that that is actually useful to the organism in some situations. Let's say when the organism is in the cold, and this is what happens. There are these little proteins called thermogenins that effectively act as uncouplers. They go and poke holes in their. They allow the transport of protons from the intermembrane space back into the matrix of mitochondria. So the outcome is heat, and that's how the organism stays a little warm when the conditions are such that when it's too cold. Now we'll look at some inhibitors of specific complexes. Some of them you may have heard. These compounds, rotenone, amytal, and demerol, will block complex 1. Cyanide, azide, and carbon monoxide, which I'm sure you have heard all of them. Like if you watch any movies, any crime movies or anything like this, cyanide is a classic poison. Taken in many Agatha Christie, mystery novels, and I know that. Azide, we use it a lot. We, meaning the food industry, for example, at some levels to preserve food. Carbon monoxide, of course, is in murder scenes where the victim is locked into the garage with the engine running of the car. That's what it does. All these things block complex 4. Cytochrome oxidase, copper oxidase. So you look at them molecularly, and they're kind of similar, right? So you have cyanide, you have azide, you have carbon monoxide, and they block the cytochromes in complex 4. So that's cool. That makes sense. Now, something that's kind of interesting, we talked about oligomycin, when we were discussing ATP synthase. It blocks the transport of protons, the translocation of protons from that is needed to generate ATP. Okay, that's what provides the energy for the soluble part of ATP synthase to make ATP. So if you add oligomycin, the protons cannot go back in. Right? Now, we've discussed how electron transport chain is uncoupled really from ATP synthesis. They're a separate system. One is making protons here, is putting protons on the outside, and the other one uses this gradient of protons to drive ATP synthesis. So what happens if you block the way of the protons to go back in? Eventually, you will also block electron transport chain because the gradient here is going to be so high that all these systems cannot keep pumping essentially more protons. It becomes harder and harder and harder for them, and at some point they will stop too. So oligomycin will also block respiration in that regard. And that concludes this video.